Okay, so we're going to take a look at a calculus question from the Nelson textbook, page 450, number 14. We're given two lines. Each one of the lines is defined using the parametric equations. So the parametric equations for line 1 are given here. X equals 4 plus 2t, y is 4 plus t, and z is negative 3 minus t. And then we got for line 2, we have x equals negative 2 plus 3s, y is equal to negative 7 plus 2s, and z is equal to 2 minus 3s. We're also told that point 1 is on line 1 and point 2 is on line 2, and we want to find these points, point 1 and point 2, such that point 1, the vector from point 1 to point 2 is perpendicular to both line 1 and line 2. So the first thing I would suggest, now I'm going to do my solution, I'll start that and use some different colors. I think the first way to start this, I would define my points. So I'm going to say that point 1 has coordinates x1, y1, and z1. And I'm going to say that point 2 has coordinates x2, y2, and z2. Now, by doing this, so far that's not going to do anything particularly impressive, but what that allows me to do is, if point 1 is on line 1, then really the only part of line 1 that I'm interested in is the part that lands on this point. And the only part of line 2 that I'm interested in is where it lands on this point. So the first thing I'm going to do here is I'm going to change my parametric equations to basically say I want to find the value of t that causes this x value to be equal to x1. So I'm going to just back that off. And so I'm going to be, when I look at my equations, I'm going to look at these equations in terms of x1, y1, and z1. And then for line 2, that's x2, y2, and z2. Now I could rewrite those equations. I'm just taking a more convenient approach here. Now there is something else that I can get from these equations, though. Because they're in parametric form, I can actually get the direction vectors for each of these equations. And the direction vectors are contained in the coefficients of the t values there and the coefficients of the s values there. And so let's take a look at the first direction vector. So this would be for line 1. Let's call that first direction vector m1. Actually, maybe let's call that d1 since I'm referring to a direction vector. So the first direction vector d1 is equal to 2, 1, negative 1, and that's from this value, and then there's a 1 here, and there's also a negative 1 there. And then my second direction vector d2 is equal to, I have a 3, and I have a 2, and I have a negative 3. So my second direction vector is 3, 2, negative 3. And now that I have my two direction vectors, and I'm told that, I think I'd like to change this if I can for point 2. Let's just erase this. Okay, so I've got my 2 points. I have my 2 direction vectors. I'm just changing things to get some consistent color coding here. So now that I've got my 2 points and my 2 direction vectors, well, what can I do with these 2 direction vectors? I am told that point 1 and point 2 are perpendicular to both line 1 and line 2. So when we think about something being perpendicular at the same time, we should be thinking of cross product. And so I've got my direction vector 1, my direction vector 2, so my third direction vector, now this is not going to be the vector p1, p2, but this is going to be a direction vector that's parallel to p1, p2. My third direction vector is going to be defined as the cross product the cross product of the other two direction vectors. So to find this, I use it's a bit of a matrix format. So the direction vector for D1 is 2, 1, negative 1, and then I also have 3, 2, negative 3, and those correspond to the I, J, and K direction vectors. And then you normally want to reproduce the I. So there's a 2 and there's a 3. And the reason we do that is for when we actually multiply these out. So let's go ahead and do that multiplication now. And so the first multiplication is going to be, this is equal to, so the first thing I'm going to find is the x component. Now to find the x component, that means I'm going to want to exclude the I part, which means I'm going to look at the j. The j and k. So I do this multiplication, 1 times negative 3, which is negative 3, and then I subtract this multiplication. So this is negative 1 times 2, so it's going to be minus negative 2. And I'm going to repeat that, so now let's undo that. Oh, unfortunately it's taking away everything. Just give me a moment here. Okay, so let's just go ahead and now repeat that. So it's this multiplication is first, this minus this. So it's going to be negative 3 minus negative 2, which is the same as negative 3 plus 2, which gives me a negative 1. And then I do for the y component, I'm going to use the k and I vectors. So now I do this one, which is going to be negative 3 minus negative 6, which is the same as negative 3 plus 6, which is positive 3. And then I finally do the I and j vectors, which gives me my k or my z component, and that's going to be 2 times 2 is 4, minus 3 is positive 1. So now I have a direction vector that is parallel to P1, P2. Another way of saying this would be that P1, P2, that vector P1, P2 is some scale factor. So I've already got S and T for scale factor, so I'm going to use the letter R. It's some scale factor times the direction vector number 3, or I could say that's R times the direction vector negative 1, 3, 1. So now that I have that, let's just take stock of the information we have. We have some sort of expression for the direction vector between P1 and P2. And that direction vector is perpendicular to both of our original direction vectors. We have these parametric equations, which we've modified to basically just say I'm just interested in the coordinates of the point, x1, y1, z1, x2, y2, z2. And so the question is, how are we going to put all of those three things together in a way that's meaningful, that allows us to solve this? Now, there are a couple of algebraic approaches that you could take. They're going to be equivalent when it comes to the geometry of the situation. But I've thought this through, and I think the simplest way to approach this is, let's go back to switch our colors again here. So I think the simplest way, actually I'll stay with green, the simplest way to approach this is to think of P1, P2. The vector P1, P2 can be represented another way as well. It's not just it's not just in terms of this vector. We also know that you can define P1, P2 as OP2, the vector OP2 minus the vector OP1. And so what is that going to be? Well, OP2 has the same components as the coordinates of P2. So that would be x2, y2, z2 minus x1, y1, z1. And of course we can simplify that fairly easily, and we end up with the x coordinate is going to be x2 minus x1, y2 minus y1, z2 minus z1. Now, to start, this just looks like we're adding an awful lot of variables, and you wonder, are we going to get anywhere with this? But now if we take a look, x2, x1, we have expressions for x2 and x1. Here they are. They're in terms of the parametric equations. They're in terms of t and s. And same thing is true for y1, y2, z1, z2. And so if you bear with me here, let's see what we can do. First of all, let's see what we can do to combine these two pieces together. So that means that if I bring those two together, then what I can say is that x2 minus x1, y2 minus y1, z2 minus z1 is equal to a scale factor r times the direction vector 1, 3, 1. Both of these are the vector p1, p2, so they must be equal to each other. But what is x2 minus x1? This might be a good time for us to actually break these out into their individual equations. So let's just look at the x-coordinate piece. x2 minus x1 must be equal to negative r. y2 minus y1 must be equal to 3r. And z2 minus z1 must be equal to r. But if we look back, we have definitions for x2 and x1. What is x2 minus x1? That's going to be negative 2 minus 4. So negative 2 minus 4 is negative 6. Positive 3s, and then subtract this 2t is minus 2t. So rather than, I'm not going to skip steps here. Let's do all of that at once. I think it might actually be useful if I were to just take a copy of this. See if I can copy that, and let's move that down because I'm going to be making use of it. Actually, I think we're going to be moving to a new page for this one, so let me just go to the next page and I'll paste that in place. Okay, so we're going to be working with that. And then we also had, just to rewrite it, we just finished saying that x2 minus x1 is the same as, again, maybe it was worth it to copy these as well. So let me copy this to the next page. Okay, so we can make use of that. And so what is x2 minus x1? So in place of x2, I'm actually going to write negative 2 plus 3s. And in place of x1, I'm going to put 4 plus 2t, and that's equal to negative r. Negative 2 minus 4, as I was saying before, is negative 6. Plus 3s, that doesn't change, minus 2t equals negative r. y2 minus y1, now that I've got these in place, they're actually a little bit easier to see. That's y2, okay? So now that I've got these in place, you can actually do this in one step. Negative 7 minus 4 is negative 11. 2s stays the same, and then we're subtracting 1t, so that becomes minus t equals 3r. And then z2 minus z1, we have 2 minus negative 3. That's equal to positive 5. Minus 3s stays the same. And then this is minus negative t, which becomes plus t equals r. So now that I've got those three equations, I might want to, let's go ahead and label this as equation 1, equation 2, equation 3. And I have three equations and three unknowns, r, s, and t. So I should be able to solve this system of equations. So taking a look across, well, I see a negative r here and a positive r over on equation number 3. So I think I'm going to take equation number 1. I'm going to rewrite it here, negative 6 plus 3s minus 2t equals negative r. And then I'm going to add equation 1 to equation 3. So 5 minus 6 is negative 1. Negative 3s plus 3s is just 0. positive t minus 2t is minus t, and I have r minus r, that's equal to 0. And so I take my t over to the other side, t, and that leaves me a minus 1. So I have my first result here, t is equal to negative 1. Now I can take that t equals negative 1 and I can sub it into either equation. So I'll switch colors here as we move to the next step in solving. So how am I going to make use of this? Well, one thing I could do is I could actually just put this t equals negative 1 into both of these equations and see what I get by way of a new simplified equation. So this one becomes negative 6 plus 3s minus 2 times t, but t is negative 1, equals negative r. And so this becomes negative 6 plus 2. So that's negative 4 plus 3s equals negative r. And then I go back to equation number 2, and that one becomes negative 11 plus 2s minus, again it's minus t, so minus negative 1 equals 3r. And so that becomes negative 11 plus 1, so that becomes negative 10 plus 2s equals 3r. So let's call that equation number 4. Call this one equation number 5. And so can we see a way to combine these together? Well, I see a 3r and I see negative r. So if I take equation number 4 and multiply it by 3, then I end up with negative 12 here. I end up with 9s, and I end up with negative 3r. So I've got positive 3r and negative 3r. So now I'm going to add these together, and I end up with negative 22 plus 11s equals 0. And so that means 11s equals positive 22. S is equal to 2. And that gives me my second value. I have values now for t, and I have values for s. I haven't solved a value for r yet, but that's simple enough to do. I can just sub into equation number 4. Equation number 4 is going to become negative 4 plus 3 times s, which is 3 times 2, equals negative r. So negative 4 plus 6 is positive 2. So positive 2 is equal to negative r, which means r is equal to negative 2. So now I have found my values for s, r, and t. Now, do we actually need all of these values? What is the question actually asking for? I'm looking back at the textbook now, and it says determine the coordinates of these 2 points. Well, the coordinates of these 2 points are going to be based upon these values, x1 and x2. Those are the x coordinates, y1 and y2. Those are the y coordinates, z1 and z2. So what do we need for those? We just need s and t. So it turns out solving for r is, from a completeness point of view, okay, that's fine, but it actually isn't necessary to solve this question. So what values do we actually get? We end up with x1 is equal to, so x1 is 4 plus 2t. You have to be careful, make sure you're subbing things in here. 4 plus 2 times t, and t is equal to negative 1. And so we end up with x1 is equal to 4 minus 2, which is 2. y1 is equal to 4 plus 1t, so that is equal to 4 plus t, which is negative 1. And so obviously 4 plus negative 1 is simply equal to 3. And z1 is equal to negative 3 minus t. Negative 3 minus t, and that's equal to negative 3 minus negative 1, which is negative 3 plus 1, or negative 2. So we now know that point 1 has coordinates 2, 3, negative 2. And we go on to do the same thing for point 2, and that's where s is equal to 2. So if I just go ahead and do this, I'm just going to do this with you verbally. If s is equal to 2, then if we sub it in here, well, 3 times 2 is 6. So negative 2 plus 6 is positive 4. So I end up with P2 is positive 4. And then if s is equal to 2 for y2, well, if s is equal to 2, this is positive 4. 2 times s is positive 4. Negative 7 plus 4 is negative 3. And finally, z2, s is equal to 2. So 3 times s is 6. So we have 2 minus 6, so that gives us negative 4. And so those are my points, P1 and P2. And I'll just go ahead and double check my answer here. And what page were we on when we started this whole thing? This was page 450. You would think I would have checked this answer before I went ahead and did the whole solution, but I'm pretty confident about our approach. And just to double check those answers again, 2, 3, negative 2, and 4, negative 3, negative 4, which is correct. Okay, so really this question, other than trying to figure out what direction to take things, this question just turns into a fairly sophisticated system of equations. So I hope that was clear, and if you have any questions about it, make sure you come and find me to ask.